electric field between the two plates. What about out here? What is my total electric field? And remember, these are vectors. Pardon?
Would it be negative now? Because it's going in the opposite direction.
The total? No. Which way are the yellow electric field lines going? That way. Which way are the green electric field lines going?
So
What is
0?
It's 0. Because they're going in opposite directions here. Over here, what's the total? I just got the hand gesture, that is correct. Someone else want to say it out loud?
0.
So if I have these two parallel infinitely large plates of opposite charges, or opposite charge density, then the electric field outside of them is 0. The electric field inside is just sigma over epsilon sub naught. Now you're thinking, oh man, the rest is obvious. I understand the entire course. So if I take these two infinite plates, this is some positive sigma, negative sigma. I got my electric field is going to the right. And I have an electric field strength of sigma over epsilon sub naught. It's just a recap of what I have written over there. Just over here, this is my electric field strength. Over here, my electric field is 0. Over here, my electric field is 0. I'm sure there's a better green. So I've got these two parallel plates. Now, having an infinitely large plate is not something that we can realistically do. The question is, at what point can we make the assumption close enough? Well, if you're designing multi-million-dollar equipment, or if you're doing engineering work and designing a fighter jet, yeah, don't make these assumptions. But for probably what most of us will do. Generally, if you look at this distance here, I'll label it something clever like D. This has a plate, let's make it a square plate, so M by M size plate. If D is much less than M, then infinite plate approximation is valid. Now, what is it? So mathematically, they'll give you a situation, and you're thinking about it and going, wait a second, what does it mean, much less than? Typically, 10% rule. So if D is less than 10% of one of those dimensions, then you're probably safe. Questions to hear? Because I'm about to introduce a new vocab word. This design here, where I take two very large plates, or at least large compared to the distance between them, this is known as a capacitor. When you're dealing with a capacitor, oftentimes you just need a symbol for it, because who wants to write out the word capacitor? And so the symbol for a capacitor is basically the design here. You take two lines that are roughly the same size, you draw them parallel to each other, and then you draw these two little segments coming off of it. This is the symbol that I will be using for capacitor. If you look at other sources, there are a couple other variations of it. Probably the most common one is something like that. This is known as a polarized capacitor. We will not deal with those. The capacitors that we have in the lab, it really doesn't matter which way you put it into a circuit. The polarized capacitor, it does matter which way you put it in. So if you run across it, sure, it is a capacitor. So if I took a capacitor, this is not one, but if I took a capacitor, most capacitors, a lot of them are round like this. It doesn't look like I've got parallel plates there. It turns out that they're still parallel plates. You take two pieces of foil or some very thin material, you put something in between it so they don't touch each other, some insulator in between so you don't touch each other, and then you roll it up very tightly. That's in essence how capacitors are made. However, how does, if I stuck something in between them, yeah, you get it closer together, but how does that affect anything? Well, let's explore that. First off, how do you charge a capacitor? Oh, yes, there is one. This is a capacitor. It is a 50,000 microfarad capacitor. It is two really thin pieces of metal, an insulator in between, rolled up. How would I charge it? Assuming this actually, I think this is a broken capacitor. But how would I charge it if it were a real one?
If it was a real one?
I mean, if it were, I think it's got a hole in there somewhere. You can burn through, there's something known as dielectric strength, which gives an idea of, you can crank up if you crank it up the voltage between these two, eventually it's going to make the jump between the two. So I think it has exceeded that, or we got it because it was dead and some industry person didn't need it anymore. All right, anyway, how do you charge it?
Connect it to a conductor.
Okay, what is the conductor connected to?
The plug in.
Okay, you can plug it in. What that's going to do is, because we have alternating current there, it's going to put a bunch of positive charge on one plate, negative charge on the other, and then it's going to flip, and it's going to flip back and forth. So plugging it in is not going to be the best solution, but it does charge it temporarily, but it'll flip back and forth 60 times a second. We will get into that in about 2 months. Just a battery. But yeah, you're all on the right track. We need to hook it to a battery. If I just took a 12-volt battery, hooked it to there, then I could charge it, in theory. But a battery, it seems like there should be some symbol for batteries, so I don't have to keep writing it. And of course, we're in luck. There it is. Now, a battery, as I hope most of you know, has a positive and a negative side. If you write a plus sign, it takes twice as much ink as writing a minus sign. This is also not a shock, unless I guess potentially you could do it differently. But a plus sign takes twice as much as a negative sign. And the reason I say that is the symbol for a battery is similar to the symbol for a capacitor, except one of the lines, the positive side, is twice as long as the negative side. They're the same size. A battery is going to look something like that. So a DC, more specifically, a DC power supply. Now, I mentioned power supply here, I mentioned battery a moment ago. Is there any difference between a DC power supply and a battery? Depends upon how picky you are. I will use them interchangeably. I have had some students who have had some electrical work, a former Navy guy, or probably Navy Reserves, where it was, he wanted that distinction. Most people don't. However, this is one of the things I'm letting go. For the people who are the purists, I should say, this is a power cell. A battery officially is more than one power cell. So sometimes you will also see that would be 2 power cells, that's a battery. I will still use this for a battery if you want to use that, or if you tack on however many of these that you want. Sure, go for it. On tests, if I'm drawing it, I will use this. If I'm doing a cut and paste from someone else's work, sometimes you'll see this. This is the positive side, that is the negative side of the battery. So if I want to hook up the capacitor to a battery, what I would throw my schematic of something like that. That should be connected. So this is a battery hooked up to a DC power supply. DC, direct current only flows in one direction. Unlike our plugs here, the current flows back and forth. Now, if I start here, let's go for a different color, stunning visual effect and all that. I start here, and I go across the battery, and I come up here, and I go across the capacitor, and I end up back here where I started. What is my change in electric potential? Yes, there's no change. I ended up back where I started. Same as if I started here and I didn't go anywhere. So if I go around a circuit, if I gain potential in one spot, I have to lose just as much potential in another spot to get back to 0 here. Well, if I'm going from a negative to a positive side of a battery, let's say that this is a 12-volt battery, then my change in electric potential from here to here, going that way, is 12 volts. If it's a 12-volt battery. If it's a 1.5-volt battery, I gain 1.5 volts. As I cruise along, remember I gain 12 volts here, going from the negative to the positive side. Cruise along here, I have to have a change of potential going across my capacitor, because I have to end up back at 0 at the beginning. So as I go across my capacitor in this direction, what is the change in the electric potential?
Negative 12 volt.
Like you mean it.
Negative 12 volt.
There we go. Because whatever I gain, I have to lose if I'm getting back to where I started. This concept has a name, of course. It is known as Kirchhoff's voltage rule. Sometimes called Kirchhoff's loop rule. There are 2 of these. There's Kirchhoff's voltage rule and current, and then there's a current rule, also known as a junction rule. But if I start at any spot in a circuit and I go around, doesn't matter how I get there, but if I end up back where I started, the sum of all my potential gains and losses has to be 0. Somehow connect this to an electric field now. I gain 12 volts, I lose 12 volts. So if I got a capacitor with a 12, actually, before I get there, on my capacitor, if it's done right, I got a positive charge on one plate and a negative charge on the other plate. Which plate is going to have a positive charge? Which plate will have a negative charge? And the answer is either gonna be right or left. To either or. Is the right plate positive or the right plate negative? Sorry, that was the left plate. Is the left plate positive or the left plate negative? Why? Is that just, pardon?
Could we censor?
No, there's more legitimate reason than that. I should say, why did you say that?
Well, I was saying that because it has to, at that point, have essentially the opposite change in, forget the words for it, delta V.
Okay,
It has to have the opposite of what happens on the battery side. So if it's going around, it's changed to 12 volts, so when it comes to that point, my brain is thinking it would be still positive, but once it passes over to the right-hand side is when it becomes, because the change happens there.
yeah, that's it. If I'm going to the right, negative 12 volts. If I'm going to the right here, I lose 12 volts, because I gain 12 volts here, I'm gonna lose 12 volts there. If I'm losing, I'm going from positive to negative. That's my positive side, that's the negative side. Let's look at it a slightly different way. Got my battery here. That's my positive and negative side. So, and if I look at a battery, there's a barrier in between. Here I got a whole bunch of extra negative charges floating around. Here I got a whole bunch of positive charges floating around. Now, this barrier here in the classic battery is as close to impermeable as you can get. So negative charges, even though they want to cut straight through here, they can't get past the barrier. So if I connect a wire to those, what's going to happen to what's going to start moving? Did you say charges? More specifically, one of those 99% rules. 99% of the time, what's moving?
Negative.
More specifically, there were lots of negative charges.
The right-hand side.
Looking for what negative charge?
The electron?
Right and left is not the right answer here. What's the classic negative charge?
Electron.
Yeah, electrons. If somebody had said that already, I apologize for missing it. Give me a couple of weeks.
That's okay.
All right, so once I connect it, once there's now a pathway, I'm gonna have electrons starting to move. So I have electrons moving out the wire, coming around, so an electron's gonna move to here, then move to here. In reality, depends on how long it's hooked up, but the electron here, if I had a battery and I had a wire touching the negative side and I just touched the plus side and took it off, these electrons would never actually make it over here. What happens is that once I make that connection, an electron will move into here, leaving a hole. That's gonna get filled by an electron, leaving a hole. That's gonna be filled by an electron, leaving a hole. And that hole is gonna start moving this way. That's the direction of the hole movement, but electrons will move in the opposite way. Sometimes I have seen in lectures where they talk about the hole movement instead of the electron movement, and I have seen that representing the hole. It's having a negative charge move this way is like having a positive charge move the other way, in case you see it. So on here, I really have electrons that are moving here. I have an electron, shut up. Dismiss. Sorry about that. I have electrons coming out the negative side. Electrons are gonna move around this way and start piling up on the plate. You get an electron here, and then a second one, and then another one. But as an electron shows up here, it's gonna drive one away from here. So if an electron shows up on this plate, an electron leaves that plate, leaving a positive behind. And so for every electron that shows up here, I have one leaving, and so that these will maintain the same charge, just opposite signs. So the negative plate is on the negative side, positive plate's on the positive side, or, as Laura had said, if I gain 12 volts going this way, I have to lose 12 volts going that way, and so I'm going from positive to negative. They work hand in hand. Any last moment questions? Luis' hat is on, he's ready to go. Cold. And he's cold. However, Thursday, Master Set 18 is due and homework quiz. It'll be a fun day, and apparently I've got an email waiting for me sent yesterday telling me that the solutions are not good.
I thought we went pretty good. I really did.
Well, it might be, but this is not an indication of it, apparently. Or maybe it's a mass hallucination.